Hello everyone, welcome back to the channel. So today we are diving into one of the most fantastic topic in machine learning, that is unsupervised learning. Okay, so now first of all you all will like that what is this unsupervised learning and why we are using it. Okay, so let me just give you a context about it. In supervised learning, which most of us probably already know, every single training has a label. Like you have a photo of a dog, so I have a label that this is a dog. When it's a spam email, you have a label that this email is a spam. But here's a problem: labels are expensive. Think about it. You have millions of images. Someone has to sit there and label each one of them. So this take time, money, and people. And sometimes the label doesn't exist at all. Okay, so what you can do in such cases? So in such cases we use unsupervised learning. Unsupervised learning is about finding the hidden structures in data without any labeling. Okay, so now let me just give you an example. Imagine you walk into a library with 10,000 books. There is no general label on any of them, like no science, no history, no romance stickers, nothing. But you have to start reading the titles and the summary to get it know that which group it belongs to. So now that's if one of them feels like for the science, one for the history, one for the romance novel. So here you didn't need any one other person to tell you that what is this. You figure it out by your own. So that's exactly was what an unsupervised algorithm does. It look at the data, figure out the grouping, natural grouping, and group it all of once. Okay, moving forward, that why this is useful. So taking it into account, number one, that it do not require any labeling cost. Like I said, labeling millions of images or documentation is expensive and slow. Second, discovering unknown patterns. This is the exciting one. Sometimes you don't even know that what pattern exists. Like a bank might use unsupervised learning to discover fraud rings, group of active accounts that behaving suspiciously together without even explicitly being told that these are the fraud accounts or not. Okay, moving towards the third point, that is compression and the pre-training. You can take a massive data like a high resolution images and compress it down into smaller meaningful representation. So this representation has become super useful for other tasks. Fourth number is anomaly detection. If your algorithm has learned what normally looks like, then anything that doesn't fit that structure is suspicious. So that's how you detect the fraud, faulty machine, and usually the network traffic, all of it. Yep. The four types, we have an overview for that. So now unsupervised learning isn't just one thing. It has four main categories. First one is clustering, grouping similar data points together. Example, customer segmentations. Second, dimensional reduction, compressing data from thousands of features just down into few. Example for this is visualizing high dimensional data. Third one is density estimation, learning the actual probability distribution of the data. Example, anomaly and the outliner detector. Fourth one is the generative model, actually generating new data that looks like your training data. This is also called as augmentation, but here what we are using is that image synthesis using a variational encoder VAE and generative adhesive networks CANs. Okay, so we're gonna start with them also. Let's move forward towards one, that is clustering. So the goal of clustering is to simply give you n data points, split them into k groups such that point inside a group are more similar to each other than to the points in other group. The most important popular clustering algorithm is k-mean clustering algorithm. The idea is that represent each cluster by its centroid, and then basically the center point of the cluster are called as mu k, and now assign each point to the nearest centroid. The steps for the given k-mean clustering are: step 1, randomly place k centroid in your data and start clustering them towards the center. Second, for each data point, calculate the distance of each centroid and assign to the closest one. Third one, now reassign all the centroids and update the centroid position. Move it to the mean, the average of all the point assigned to it. Fourth, repeat this step 3 to 4 times iteratively until you get the same clustering after the centroid assignment. Okay. So now we have a big question that how to choose the value of k. So you run k means for k equals to 1 2 3 4, and you plot the inertial j on the y-axis and k on the x-axis. As k increases, j always decreases. That's obvious. More cluster points mean that you are more closer to the centroid. But at the same point, the improvement start flattening out. That the elbow point where the curve bend. So that's your optimal k. Okay, so we have a picture of about how k-mean clustering has been done via scattering plot. You can see about the each of the centroid mu1, mu2, mu3 are given. Yes, so now let's move forward towards one more part of it where k-mean clustering is facing two big problem. So that can be solved by DBSCAN. Now what it does it that in k-mean clustering we have two big problems. One, that it work only with the spherical round clusters. If your cluster are weirdly shaped like a ring or anything else, then k-mean struggles over that. Second point is that you have to tell it k upfront. Sometimes you don't know how many clusters are there. So here we have DBSCAN. It is density based partial clustering of application with noises. The key idea is simple. A point belonging to a cluster if it has at least min sample neighbor with a radius epsilon. If a point doesn't have enough neighbor, then it is labeled as noise. Okay. So in this process, the grown cluster from a denser area and automatically label the points as outliner or not. There is no specific need of k for this. Okay. On quick comparison, we can see that the k-mean clustering only handles the spherical spherical shapes and the spherical data, while the DBSCAN can handle arbitrary shapes also. There is no need of k, and it can handle the outliners naturally. Moving forward towards the dimensionality reduction. Okay, real world dataset can has thousands of feature. A single image might be 224 by 224 pixel and over 150k number of pictures. Okay, working direction with this is slow and noisy. Dimensional reduction compress all these feature down to a small number of meaningful dimensional dataset. Okay, so for that we have PCA, principal component analysis. This is the topic which we are going to cover just after this video. PCA is a classic algorithm for it. The idea is finding the direction in your data where the variance is maximum and where the data is spread out the most, and projecting them onto the direction. So these directions are called as the principal component. Okay, the steps for principal components are being given here. Step 1, center the data, subtract the mean from every data point so your data is centered at 0. Second, compute the covariance matrix. This is the matrix that capture how every pair of feature varies together. Mathematically, it's 1 by n times x transpose times x. Okay. Third step is eigen decomposition of the covariance matrix. This will give you the eigenvectors, the principal component directions. Okay, that how much variance each direction capture. Step 4 is project the data onto a top d eigenvector. You're gonna see that maybe thousands of features just go down to d features. Here's a nice interpretation that the j principal component explain lambda j divided by the sum of all the lambdas of the total variance. So you have to speak that I am keeping the top components that explain 95% of the variance at a very common choice. Yes. So here's a visualization for the PCA, that how it can be seen about the perpendicular lines, the arrow pointing and showcasing the variance, maximum variance, direction of the maximum variance and all that. Yes. Moving forward, we have the t-SNE plot. Okay. Now PCA is linear, so it can give around a straight line data. But what if the data has complicated curve structure? So that's for that we have the t-SNE, the t distributed syncrotic neighboring embedding. Okay, so TCNE is a non-linear method. It designed to take the high dimensional data and plot it into a 2D or 3D visualization. The key property is that it try to keep the neighboring points in a original space nearby in a 2D projection. Okay, it preserve local data nearby also. So there's a quick thumb rule for this, that you use PCA when you have to feed features into another model or keep it a linear structure. Secondly, use t-SNE for the visualization to see the natural clustering of your data in a 2D plot. Okay. Moving to section 4, we have the density estimation and the anomaly detection. So this is really cool. The goal is to actually learn the probability distribution of p of x from the data. Once you know p of x, any point with a low probability is an anomaly. It doesn't fit the normal distribution of data. Gaussian mixed data is GMM. Okay, it's a Gaussian mixture model. The idea is assume your data was generated by k Gaussian distribution mixed together. Each Gaussian has its own mean mu k and covariance sigma k, and each has a mixing weight pi k. Now, how much of the data comes from that component? Sum it all pi k's sum up to 1. So the overall density of the weight sum to k Gaussian. Okay, now the steps to learn for the parameter using the EM algorithm, expectation maximization, which has two steps. E step, for every point compute the soft probability that is belonging to each component, and now a hard assignment is that the probability, for example, this point is 70% cluster, so it goes to 1, and 30% cluster goes to 0.2. Second part is the M step. Use this probability to update the mu k, sigma k, and pi k to maximize the likelihood of the data. And you have an alternative between E and M until converges. Okay. Key difference for the key mean, that k mean gives harder assignment, each point belonging to exactly one cluster. GMM give soft assignment. GMM is more flexible. Okay, it can model elliptical clusters, not just the spherical structures. Okay, we have one more topic, that is the isolation forest, but isolation forest is not usually so important. You can just get it like that when we build random trees, so at each node we pick up a random feature and randomly split them. Okay, but now in an isolation tree you already have the idea that which split is being surrounded by what points. Okay, so that's simply the ideation behind the isolation forest. There is nothing so much, but it's just simple, fast, and work really well. Okay, we have one more important section, that is the autoencoder. Now in the neural network approach of unsupervised learning, an autoencoder is a neural network with a specific structure and a very clever training trick. The structure has two parts, encoder and decoder. Encoder takes the input x, which can be counted at high dimensional images, says thousand of images, and compress it down to a small latent code x, latent code z, maybe just 32 dimensions. The decoder takes the latent code z and tries to reconstruct the original image given your x hat. The training objective is very simple: minimize the reconstruction error, which is square difference between the x and the x hat. Okay, now the real magic is that there is no label needed at all. The target output is just the input itself. The network learns to compress and decompress on its own, and just because d is much smaller than d, the bottleneck in the middle, the network is forced to learn a meaningful compact representation of the data. It just can't memorize, it has to learn the structure. Okay, so the applications for the autoencoder are that it is being used in denoising, it is using anomaly detection, and it is using pre-training for the generative part. I have already told you about the variational autoencoder VAE that learns and smooth the continuous latent space. Okay, now we have some of the practical tips. Okay, so we'll go into it. Let me give you a practical tip that so first, what actually matters when you are building these things. Tip 1, always scale up your feature. Seriously, always clustering and PCA both are very sensitive to the feature scaling. So feature scaling and feature engineering is one of the most standard part. Second, choosing the value of k. So k is being used as a hyperparameter in the k mean clustering, so you have to choose it properly. PCA before clustering. Always before clustering, you need to reduce the dimension to keep enough of the component to retain about 95% of the variance. Fourth tip is for the t-SNE plot is only for the visualization. Don't use it repetitively, and because its output get into a downstream model. Okay, step 5 is use GMM when clustering overlaps. If you cluster are not nicely separated or have a different shape and size, GMM will outperform the k-mean cluster. Okay, sixth is validate without label. You don't have labels, so the whole point is that use the internal matrix like the inertia and the Siloite score for clustering, reconstruction of the loss for autoencoders, and likelihood and log likelihood for GMM. Okay, Here's a quick summary is given about what we have covered. We have covered the K-mean, DBSCAN, PCA, t-SNE, GMM, autoencoder, isolation forest and all. And a key takeaway about each of the points which we have covered. So wrapping up the unsupervised learning lecture, we have covered everything from the basic intuition with the library example to the way to K-mean clustering,